Hello, my name's John. We're going to be doing some work on statistics on probability distributions in the next few videos. The target is really for first year or maybe going into second year further maths students studying for the statistics module. And certainly the particular students I'm thinking of have already done the discrete random variables and as part of the first year AS further maths and AS single maths. So the kind of students I have in mind have done their first year work really on statistics individually on the single and further maths, and then going on to do in the second year work on statistics as part of single maths and further maths. More immediately, what's going to follow this is what we're heading towards is work on normal distribution, which is on single maths, but say I'm targeting it to further maths students so that you can see the wood from the trees a little bit more, because what happens too much as maths teachers, I think, is we just teach you little bits and pieces, and not often enough do we kind of give you an overview of the kind of distributions of everything that we have done and everything that we will do, and that's the purpose of this. So one of the things that one really important distinction between data and distributions is whether it's discrete or is continuous, and the way we deal with data is very different if we've got discrete or continuous data. And as I say, we've already, or should have already, covered the work on discrete data. And we will come on to work on continuous data more immediately. The normal distribution will be the first thing we cover, but then in future weeks and months, maybe up to a year, no, it will be less than a year, exponentially uniform distribution for continuous distributions. Okay, but I just wanted to just give you that overview. These are the four that were particular distributions. It doesn't mean to say you couldn't be defined a distribution, given a distribution that isn't one of these, but these are the four that we should be familiar with. And just a reminder, a discrete distribution, you might have seen it in, this is a discrete random variable. So suppose we've got four possible outcomes, four possible numbers, and these are our numbers x, and we've got probability the random variable x is equal to x, and that could be, I don't know, that could be a half, and this could be 1, 6, 1, 6, 1, 6. That is a discrete random variable, but it's not a particular, it doesn't have a particular name to it, but it is discrete because you've got regular, it can only take particular numbers, and that's what we mean by discrete. Not always whole numbers, but it only can take only particular numbers. Can a discrete take, whereas a continuous can take a range, and not necessarily every number, but it can take a number within a particular interval, particular interval. So that's what we're dealing with here. So here we go. Binomial is part of single maths, but you could see in further maths, of course, as well. That's probably the most common one that we look at with discrete random variables. It's got two parameters, n and p, and it's got this thing called a probability function. Probability, if we call x the particular value, we're finding probability of x taking a particular value. Probability x is equal to x is n x, and then we've got p to the power of x, and then 1 minus p to the power of n minus x. So complicated, but I'm sure you'll know, because we've sort of done it already, it's not actually particularly complicated. And then Poisson's got one parameter only, lambda, which is the rate of something occurring. And the formula for that is probability x is equal to x is equal to e to the minus lambda, lambda to the power of x over x factorial. Okay, that's the Poisson formula that we do. You are given these, I believe. Geometric, that's to do with when you're it's a kind of function that has this kind of thing called lack of memory property. It's basically when you're waiting for something to occur, so it's the number of occurrences before something happens. So for example, so someone throws a fair dice, and n could be defined as the first time to get a 6. You could get it the first time if you're lucky. There's a 1 in 6 chance of that, but you might come the 4th, 5th, 6th, 7th, or even much later and later than that. To anyone who's played a game where you have to start with a 6 will know this. You might get it first time. You might be taking 15 odd times to get it, and that's what we call the geometric distribution, and that has probability function. Probability of the random variable x equals to x is equal to, well, what you need is to have p it not to occur x minus 1 times, so it doesn't occur x minus 1 times, and then on the x time it does occur p. So that's the probability of it occurring on a particular value x. The uniform is, let's say, boring one really. N is just the number 1 to 1. Those are the possible numbers up to n, and they're all equal, so it's 1 over n. Okay. Now the key thing is here, it's discrete. So if we were actually drawing a graph of these, for example, this might be a binomial, something like that. Doesn't have to, it takes particular values, or this might be the Poisson. They look different, obviously, compared to the distribution. This one might be, we might have a geometric. One property that's interesting about a geometric, it's a bit of an aside really, is that the mode is also always the first one, even if it's a low probability of it occurring. So even so, for example, in the national lottery, which you've got about 1 in 13 million chance of winning, and we define the geometric distribution the number of times it takes me to win in a lifetime. It's probably you're not going to, but imagine you just carry on forever till you actually win. The most likely time to win is the first one, which is kind of, I always think is quite nice. It's to do with a lack of memory property and various things, and it's counterintuitive, but if you think about it, we're not talking about it being particularly likely it happens the first time. It's just that, say, as opposed to the 100th time, or the 1000th time, say, the 1000th time. Well, the first time it's got to happen is 1 in 13 million chance. In order for the 1000th time to happen, it has to have not happened the first 999 times, and then it has to have happened on the 100th time, which is by definition going to be less. So we're not talking about it being likely, more likely to get it first time than after the 1000th time. It's just more likely to get it the first time than exactly the 1000th time. So the mode is always the highest value, which I always think is quite an interesting thing. But anyway, I digress. I really want to emphasise the fact that you kind of got these stick graphs or bar graph or whatever. Normally we could represent it with a bar graph with gaps in it, but the point is we're talking, that's how we represent it if we wanted to represent it graphically. Okay, so we should be familiar with those 4 types of distribution and the idea of discrete random variables and the probability function. You might not be called probability function, but it's sometimes called the probability function that we're dealing with here. Right, so moving on, the probability density when we're talking about continuous random variables, we're dealing with this thing called a probability density function. Basically, it's a graph, and we're talking about the area underneath the graph. I'm going to explain that a little bit more in the next video, but we're not talking about individual values here. We're talking about the probability of it taking a range of values in between, a particular that it falls between it 2 particular values, not one individual value. In fact, when you talk about continuous, this is something I've had. Sometimes some students take some convincing, but the probability of getting it bang on with a continuous distribution, a particular value, an exact value, is 0. So that is something that's a bit counterintuitive. So our thing will look much more like this thing will be, we talk much more about range of values, and we also can be a little bit more lackadaisical about whether we're dealing with strict or inclusive inequalities. You know, it really makes no difference with a continuous random variable, really. Well, sometimes we probably best stick with the same convention, although I have to admit I get very lazy and change them, and nice students sometimes. But actually, whether it's strict or inclusive makes no difference with a probability density function, with a continuous random variable, as defined by a probability density function. So that's important. The probability of getting bang on a value is 0. That's quite important, really important, in fact, that you got that idea. It's all about range of values. So, and what this probability density function actually gives you is a probability that it lies between these two values, but you actually have to integrate, as we'll see in the next video, to actually find the probability of something happening. But there again, with the normal distribution, which we'll see, it's the probability density function isn't terribly helpful, as we will see. So let's move on to the exponential distribution. That's one it's almost like a continuous. There's a connection with both the Poisson and geometric. The lambda is very much connected to the lambda value there. It's about something happening at a particular rate, but the time taken or the distance before it happens. So basically, you know, buses come along, arrive at a particular bus stop on average once every 20 minutes, and we can model that as an exponential distribution for the time to wait for the first bus. You might be lucky and you get there straight away, but you might be unlucky. I'm not sure a bus stop actually think about as a good example, because that would question the randomness, because that would be following a timetable. So I'm not going to cut this because that's not the best of examples, because it has to be random, a bit like the Poisson. So yeah, maybe just talking about first time you see it, if you're looking in the night sky, the time it takes to see the first meteor in the night sky, that would be more of a random occurrence, and the time it takes to see it. So say if you for every time you're looking in the sky at night, we say the first time, you know, it normally takes about 2 hours to see a meteor coming through the sky, and we could model this as we could model the time as exponential as the time it takes to see the first one. You might be lucky, see it straight away, or you might be there all evening, following evening after that, and not see one. Okay, I'm not talking about the cloudy skies. Hopefully you've got the idea. Right, so the exponential distribution, the probability density function, fx, which remember is all about, it's all kind of related to finding this, although we will need to integrate this to find this. For a probability density function is lambda e to the minus lambda x. Well, it might be, it's often written as t there because it does often involve time, like my meteor example or whatever. And the uniform distribution, it's got a constant. That one basically, a bit boring. The probability density function, it's always got the same probability there, and the 1 over b minus a. Now, I don't want you to worry too much about this, because I'm going to talk about probability density functions in more detail in the next video. But that pretty well, those 7 distributions are pretty well the 7 distributions that if in your exam the name was just mentioned to you, you would have not a leg to stand on and said, oh, I've never heard of that before, because these are the 7 distributions that are specifically mentioned that you need to know. And I believe that the formulas for most of them, if not all of them, are actually given to you in your formula booklet. You might say, you might wonder why I've left this probability density function out for the normal distribution. That's because I don't remember what it is. I just know it's very complicated. I know it involves eta minus x squared. I think what I'll do now is actually pause, and I will show you on the screen, and I'll get it up on the screen in a moment. But actually, as we'll see, it's not that helpful. So although the probability density function is how we generally define continuous random variables, model them. The particular probability density function for the normal distribution is fiendishly complicated and actually impossible to integrate. But we'll see that in the next video and the following video. I will mention that again. But as I say, I will show you the actual probability density function for it now. So hopefully you'll forgive me for not knowing it off the top of my head in the previous section. That is the probability density function for the normal distribution with parameter mean mu and standard deviation sigma. And as I say, to actually integrate that function is, well, actually algebraically it's impossible. So we'll be using a calculator for that. So we don't need to be able to integrate. But basically, I wanted you to see the function before as part of this general summary of our distributions. Our next video is going to actually take a more general look at probability density functions and continuous distributions, only briefly, and then in the video following that we'll be introducing this normal distribution, which, as I said during the video, is really perhaps the most important distribution there is in the whole of statistics. Okay, right, I think that's time to stop. Cheerio.